over the closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught into d phi E by dt. In earlier lessons, we have learned that charges at rest produce an electrostatic field, and charges in a steady current carrying conductor produce a constant magnetic field around it. But Maxwell explained that accelerating charges produce both an electric field and a magnetic field that varies with respect to time. And these fields propagate in the form of a wave called the electromagnetic wave. To explain the production of an electromagnetic wave, let us consider an oscillating charge, which refers to an accelerating charge, oscillating along the y-axis with some constant frequency. The oscillating charge produces an oscillating electric field along the direction of the oscillations of the charge and propagates along the x-axis. Here, the frequency of the electric field is equal to the frequency of the oscillating charge. We know that an electric field changing with respect to time produces a magnetic field. The oscillating electric field produces a magnetic field which oscillates perpendicular to the direction of the oscillations of the electric field, that is, along the z-axis, and propagates along the direction of the x-axis. Now, the oscillating magnetic field produces an electric field which is oscillating perpendicular to the direction of the oscillations of the magnetic field and propagates along the x-axis. Thus, the oscillating electric field and the oscillating magnetic field regenerate each other and propagate along the x-axis. This wave is called an electromagnetic wave. Its frequency is equal to the frequency of the oscillating charge. According to the law of conservation of energy, the energy lost by the oscillating charge converts into the energy of the propagating wave. We know that visible light is an electromagnetic wave with frequency in the order of 10 power 14 Hz. Is it possible to produce visible light with an AC circuit in which the current oscillates with a frequency equal to that of visible light? The maximum frequency that can be produced with modern electronic circuits is in the order of 10 power 11 Hz, whereas the frequency of visible light is in the order of 10 power 14 Hz. Hence, visible light cannot be produced in an AC circuit with oscillating currents. From the above discussion about electromagnetic waves, it is clear that the electric field E and the magnetic field B oscillate perpendicular to each other and perpendicular to the direction of propagation of the wave. Now, let us discuss the mathematical analysis of the electromagnetic wave. As the wave propagates in the direction of x-axis, the electric and magnetic fields oscillate along the y-axis and z-axis respectively. These fields vary sinusoidal along the x-axis with respect to time. The electric field and the magnetic field can be written as EY is equal to E naught sine kx minus omega t and BZ is equal to B naught sine kx minus omega t respectively. Let these be equations 1 and 2 respectively. Here, E naught is the maximum value or amplitude of the electric field. B naught is the maximum value of amplitude of the magnetic field. And K is the wave number related to the wavelength of the wave, lambda. That is, K is equal to 2 pi by lambda. Let this be equation 3. Omega is the angular frequency. It is related to the frequency of the wave by the equation omega is equal to 2 pi nu. Let this be equation 4. On substituting equations 1 and 2 in Maxwell's equations for electric field and magnetic field, we get a relation between omega and K as omega is equal to Kc. Let this be equation 5. Here, c is the velocity of electromagnetic wave that is equal to 1 by square root of mu naught epsilon naught. On substituting the equations 3 and 4 in the equation 5, we get c is equal to nu lambda. From Maxwell's equations, we also get the relation between the maximum values of the electric field and the magnetic field as E naught by B naught is equal to C. That is, the ratio of maximum value of the electric field to maximum value of the magnetic field of an electromagnetic wave is equal to its velocity. We have learnt about the different types of waves. Sound waves in air are longitudinal waves that propagate in the form of compressions and rarefactions. Water waves on the surface of water are transverse waves. It propagates in the form of crests and troughs. This shows that waves propagate through a material medium. In the early 1800s, scientists believed that there must be a material medium spread throughout the space in which an electromagnetic wave propagates. That material medium, which spreads across the entire space, was called ether. Later in 1887, Michelson and Morley conducted an experiment in which they proved that ether does not exist. Thus, the electric and magnetic fields of the electromagnetic wave oscillating in space with respect to time are self-sustaining. The electromagnetic waves are thus different from other waves, such as sound waves or water waves. Let us discuss them briefly. The first important feature of electromagnetic waves is that they can propagate in vacuum. That is, a medium is not necessary for the propagation of electromagnetic waves. From Maxwell's equations, the velocity of electromagnetic waves in vacuum is written as c is equal to 1 by square root of mu naught epsilon naught. Electromagnetic waves can also propagate in a medium. For example, light is an electromagnetic wave that can propagate in vacuum and in media like glass and water. When the electromagnetic wave propagates in a medium, the electric field and the magnetic field of the wave are described in terms of permittivity epsilon and the magnetic permeability mu of the medium. Hence, the velocity of an electromagnetic wave in a medium is written as V is equal to 1 by square root of mu epsilon. By this expression, we can conclude that the velocity of electromagnetic waves in a medium depends on the electric and magnetic properties of the medium. When light travels from space into a medium, the light gets deviated from the original path. This deviation depends on the refractive index of the medium. Refractive index of a medium is defined as the ratio of velocity of light in vacuum or free space to the velocity of light in the medium. Consider n as the refractive index of a medium, v as the velocity of light in the medium, and c as the velocity of light in vacuum. Then the refractive index n is equal to c by v. In vacuum, the velocity of electromagnetic waves is a constant. Even for electromagnetic waves of different wavelengths, the velocity is the same. Its value is 3 × 10⁸ meter per second. Since the velocity of light is a constant, it is used to define the standard unit of length, that is meter. 1 meter is defined as the distance travelled by light in vacuum in a time interval of 1/c seconds, where c is the velocity of light in vacuum. In general, waves carry energy and momentum from one place to another place without the actual motion of the particles of the medium. Similarly, electromagnetic waves also carry energy and momentum. We have learned that the energy density associated with the electric field in free space is written as UE is equal to epsilon naught E square by 2. And the energy density associated with the magnetic field in the free space is written as UB is equal to B square by 2 mu naught. As an electromagnetic wave is a combination of electric and magnetic fields, it carries energy and momentum. This presence of energy and momentum in an electromagnetic wave can be understood by considering some charges in a plane which are perpendicular to the direction of propagation of the electromagnetic wave. The charges are set in motion by the electric and magnetic fields of the electromagnetic wave. Thus, the charges acquire energy and momentum from the electromagnetic waves. Since the electromagnetic wave carries momentum, it exerts pressure called radiation pressure. If U is the energy transferred to a surface by electromagnetic radiation, C is the velocity of the radiation, and P is the momentum exerted by the radiation on the surface, then P is equal to U by C. Here, the momentum P is inversely proportional to the velocity of the radiation C. Since the value of C is very high, the momentum exerted by the electromagnetic radiation is negligible. The radiation pressure exerted by the visible light is determined by calculating the momentum using the formula P is equal to U by C. The radiation pressure of visible light is in the order of 7 × 10⁻⁻⁶ Newton per meter square. Different types of electromagnetic waves that carry energy and momentum are useful in various applications, which we will discuss in the other module.
There are different kinds of electromagnetic waves in nature. The arrangement of these electromagnetic waves in accordance with their increasing or decreasing order of frequency or wavelength is called the electromagnetic spectrum.